Okay, in this video I'm just going to go through the main points of kinetic molecular theory again, and just sort of talk about what those mean, and then go to the kinetic molecular theory, how it's sort of changed for ideal gases. So, first of all matter is made up of particles. Regardless of the substance or anything, the one thing that's always consistent, regardless of whether we're dealing with gases or anything else, is that even though we can't see them because they're too small, we understand that all matter is made up of particles. It could be something like a metal where we have these little positive ions that represent the particles with electrons around them, or something like a liquid, say like water, where we have individual particles that look like this. And they sort of interact with each other, but they're not in a regular crystal lattice. Or something like a gas, like something like O2, where the particles are flying around completely independently, totally far away from each other, not having anything to do with each other. All matter is made up of particles. Different types of matter has different types of particles. So these are sort of what the particles look like in a metal. This is what it looks like in water, and this is what it looks like in oxygen gas. So when we say something is a different substance, what we mean is that the particles that make up that matter are all different types of particles. The particles are constantly in motion, so I think it's easy to see how the gas molecules are constantly in motion, flying around, not really interacting with each other, or even the water molecules that, while they stick together, can sort of slide past each other and rotate and all that. But it's important to remember that even in a solid, those individual particles will vibrate. They'll go back and forth and back and forth and back and forth about their mean position, and they'll go in all the different directions, right? So this particle can go back and forth like that, or up and down, back and forth, and he can vibrate around. As long as he stays in that same basic location, he can vibrate even if he's in a solid. We say liquids will vibrate and rotate, which lets them flow past each other. And we say that gases can translate from location to location, actually physically flying about inside the container. And finally, there are attractive forces between the particles. In solids, we say the attractive force is much greater than their kinetic energy. And so the solids remain bound in location. The particles in a solid remain bound in a location by those forces. Okay, sorry, I had to pause there because I was having a little bit of a battery issue, but here we go. Okay, so I was saying that in solids, the force is very strong in comparison to the kinetic energy, and so these molecules or these particles are held in their place by the force, and so they can vibrate, but they can't move around. In a liquid, the intermolecular force is sort of closer to the amount of kinetic energy. And so the two factors are sort of competing with each other. That means that liquids can flow. The particles stay together, but they're not bound to the location. So they're not kind of stuck in an individual spot there. What that means then is these water molecules can slide past each other, and that will allow the liquid to flow. The particles do stay in the same basic general region, though, and that's why their kinetic energy is enough to let them slide past each other, but it's not enough to get them to evaporate into the surroundings or to go out into the air and fly around as a gas. Finally, in a gas, the force is less than the kinetic energy. And here the particles are moving so much that they fly apart. They fly around the container, and as a result they fill the container. Okay, so that's just a quick review of kinetic molecular theory in the first place, the four main ideas. how does that apply to gases? So let's look at gases a little bit more specifically. And when we do that, we come up with the kinetic molecular theory of gases. It has 5 points. The first one is that since these particles fill their entire container, and they're so small in that container, we basically can treat their volume as if it's 0. We know the volume of these particles isn't really 0, but basically what we're saying is these particles are not occupying space because they're running into each other. The reason that they occupy space, so the reason that the thing that sets how big the container is their physical collisions with the side. So again, because they're so small in comparison to the distances in between them, it becomes easy to basically treat them like they have no volume. There are not attractive forces between the particles. If you imagine for this thing to have become a gas, the force already had to be less than the kinetic energy. But then if we also consider that these intermolecular forces are related to the distance between the particles, as distance between particles grows, the force decreases. Once the forces were already low, and that's what let the particles escape the material. But once these particles get far apart, now they have huge distances in between them, and these forces go down even further. Again, it becomes reasonable once they become a gas to basically treat it as if there is no force. Because it gets so small, we can say it is officially completely insignificant. So if there's no forces acting on these guys, they're kind of like billiard balls bouncing all around the table. We're just going to treat them like these things that fly very fast in straight lines. So here's my gas molecule. He's flying fast this direction until he hits the wall where he's going to bounce back that way. Maybe this guy's flying fast in this direction, and they're all translating in these straight lines basically, banging into the sides of the container. Which brings us to our next point. When they bang into the side of the container, we consider those collisions to be elastic. What does elastic mean? It means they don't lose any motion when colliding. Sorry, motion not lost. So maybe they give their speed to another gas molecule, or they give their speed to the wall, but the overall amount of energy stored up as kinetic energy or stored up in motion energy stays constant during the collision. So what elastic really means is that kinetic energy is conserved. But that's a little confusing. What that means, kinetic energy is motion. And so the total amount of the motion of the system is conserved. So when these things bang into the wall, they don't transfer their energy to heat or sound or any of those kinds of things, but they just keep bouncing, or light or any of those kinds of things. They just keep bouncing around back and forth, maintaining their energy as motion energy. Finally, the average kinetic energy of the gas molecules is directly related to the temperature. So what we say here is that as the temperature increases, what we really mean is the speed of the particles is increasing. So hotter, in terms of a temperature that we measure on a thermometer, what that really means is faster particles. Again, we need to be clear here, there's a lot more going on with temperature, and as a result, I'm going to save that for a separate video. So here are basic rules that apply to all matter. All matter is made up of particles. Different types of particles different types of matter has different types of particles. The particles are in constant motion, and there are attractive forces between the particles. And here are how we adjust those rules to deal with gases, making some assumptions here that aren't completely true, but are close enough to true that they help us handle how gases behave fairly accurately. The volume of a gas particle is so small we treat it as having no volume. So essentially the space between them has gotten so big that their size doesn't matter. There are no attractive forces between the particles. Again, the distance between the particles has gotten so large that that force has gotten so small that we can consider it to be ignorable. Gas molecules move fast in all directions in straight lines, so if there's no forces acting on them, they're just going to keep flying around. When they collide with each other or the side of a container, the motion energy they have, or the kinetic energy they have, is not lost in the collision. The special name for that is that it is an elastic collision. And finally, that temperature is directly related to the speed of the molecules. So a higher temperature means that in general, the particles in that substance will be moving faster. Again, I'm going to do another follow-up video right now that talks about temperature in a little bit more detail.